Hi, I am Wenyue Zhao. I will be presenting our work, Mitra, a framework for multi-instance graph traversal. This is a joint work between Huawei Edinburgh Research Center and the University of Edinburgh. In this work, we propose Mitra, a framework for computing multi-instance graph traversal algorithms. First, let's start with background information. Given a data graph G, a graph query Q can be sparse matrix, vector multiplication, personalized PageRank, shortest path, etc. Traditionally, a graph query Q takes a single input source vertex. In this work, we consider multi-instance processing, computing results for graph query Q with a set of input source vertices S1 to Sk. Many application scenarios require answering batches of graph query instances over huge graphs, which requires efficient multi-instance processing. So what is the difference between multi-instance processing and traditional single-instance graph query processing? Well, multi-instance processing provides the opportunity of sharing across instances. Here is an example. On the left, we have input containing a data graph G. Graph query Q is BFS, and we have two query instances with different source vertices, V1 and V2. For single instance processing, these two instances are processed one by one independently. We first start BFS from source vertex V1, traversing edges V1 to V3, V1 to V4 in round 1. In round 2, we traverse edges V3, V5 from vertex V3 and edge V4, V5 from vertex V4. In round 3, since vertex V5 and V6 have no outgoing edges, we stop. Afterwards, we run BFS from source vertex V2. In this process, we have 8 edge accesses in total, 4 for each source vertex. Now we consider multi-instance processing. In round 1, we start from both instances, V1 and V2 together, traversing 4 edges to V3 and V4. In round 2, they both visit V3 and V4 and can share traversal for edge V3, V5 and edge V4, V6. In round 3, we stop. In this way, 2 redundant edge accesses are avoided, resulting in 6 edge accesses in total. Current approaches for multi-instance processing fall into 2 categories. The first one is to use general-purpose graph processing framework, running query instances one by one independently. Many frameworks have been proposed for shared memory or distributed environment. They're easy to program, but less efficient due to lack of sharing. The second one is to use crafted multi-instance processing algorithms like multi-source BFS, multi-source Dijkstra. They run multiple instances in one go with computation sharing across instances. They are more efficient, but highly specialized. So can we have the best of both worlds? In answer to this question, we present a Mitra, a multi-instance graph traversal framework. Let's start with the frontier ranking model, which is the foundation of Mitra. Recall the previous multi-instance processing example. We are running 2 BFS query instances from source vertices V1 and V2. For each vertex in the data graph, we attach a pair of numbers as shown in the data graph near each vertex. These numeric vertex properties are called vertex rank. The first number corresponds to instance S1 and the second one corresponds to S2. Before round 1, all unvisited vertices have their vertex rank value set to infinity, and source vertices set vertex rank value to 0 for corresponding instances. V1 for instance S1 set first vertex rank value to 0, and V2 for instance S2 set second vertex rank value to 0. As shown below the data graph, we have an active frontier containing a set of vertices. Before round 1, we add source vertices into next frontier, V1 for instance S1 and vertex V2 for instance S2. Now let's walk through the vertex ranking process. In round 1, we explore vertex V1 for instance S1 in active frontier, traverse edge V1, V3, and edge V1, V4. We set the vertex rank value to 1 for instance S1 and add neighbor vertices V3 and V4 to next frontier for instance S1. We do the same to vertex V2 for instance S2. In round 2, we explore active frontier containing vertex V3 and V4. The active frontier indicates traversal is ready for both instances S1 and S2, so we share the traversal of edge V3, V5 and edge V4, V6. We set vertex rank for V5 and V6 to value 2 and add them to next frontier for both instances. In round 3, we find no outgoing edges and BFS for both instances stop. As we can see, the pattern in this frontier ranking process is that we have vertices grouped into frontiers based on their frontier rank value, and in each round, we are visiting vertices from the active frontier and traversing its neighboring edges, updating vertex rank and frontiers at one time. We have 3 parameters for frontier ranking model: vertex rank, frontier width, delta, and frontier structure. In this example, we are using number round as vertex rank, frontier width 1, and frontier structure list. Varying these 3 parameters, frontier ranking model can express many graph algorithms like sparse matrix vector multiplication, personalized PageRank, Dijkstra, both single instance and multi-instance version. We proved that our frontier ranking model is more expressive than existing vertex-centric frameworks. Now let's see how frontier ranking model provides an abstraction for graph query, separating traversal logic and computation logic. We have 3 parameters, as we said before: P1 for vertex rank, P2 for frontier structure, and P3 for frontier width. Graph query traversal logic is captured by the vertex ranking process. In each round, we traverse vertices in current active frontier Fi and assign vertices to future frontiers according to their frontier rank value. Traversals are aligned and shared across multiple instances. When traversing edge E, edge function Fe is invoked, sharing computation across instances. Query-specific computation logic is expressed in edge function Fe. We demonstrate how to program with Mitra using this example. User first choose the 3 parameters for frontier ranking model, as shown in line 1 with blue rectangle box. Then, user follow textbook graph algorithm to implement their edge function. The only difference is that user should replace operators using Mitra operators. In this example, replace add with Mitra add and replace min with Mitra min. The simplicity of programming with Mitra is also reflected in lines of code required. Compared to crafted one-off multi-instance processing algorithms, Mitra only need about 20 lines of code for the entire program, while multi-source BFS use over 500 and multi-source Dijkstra more than 200 just for the core function. Now let's take a closer look at the architecture of Mitra framework. This diagram shows how Mitra framework works under the hood. On top, we have user interface for user to configure frontier ranking model by choosing parameters and plug in graph application code to express application-specific computation logic. In edge function, arithmetic operators use Mitra operators provided by Mitra library. For the traversal logic part on the left, Frontier Ranking Model Manager takes user-provided configuration. Traversal function carry out graph traversals by exploring and updating frontiers. When traversing an edge, traversal function call edge function implemented by user to invoke computation. Optimizations including track-free and SIMD are applied behind the scenes. Track-free can bypass traversal progress tracking for each instance if not necessary in graph algorithm. SIMD refers to single instruction multiple data. It is embedded in Mitra operators and can work with or without track-free. It is implemented using Intel SIMD intrinsics. In summary, Mitra synthesize multi-instance graph algorithms and apply optimizations. Next, let's see performance evaluation results. We use 8 real-life data graphs for testing, as shown in the table on the right. We compare 3 types of algorithms for multi-instance processing. The first one is serial algorithms implemented in Ligra graph processing framework. The second one is crafted multi-instance algorithms, multi-source BFS and multi-source Dijkstra. We are using their open source versions. And finally, Mitra multi-instance algorithms. We vary the number of query instances from 16 to 256. On average, Mitra achieve an order of magnitude speed up over serial algorithms. As shown in the charts on the left, Mitra outperforms serial algorithm significantly and is comparable to crafted multi-instance algorithms. This is confirmed by number of accessed edges charts on the right, indicating level of sharing for each algorithm. We observe similar results on other data graphs as well. We also evaluated the effectiveness of optimizations. We found that SIMD achieved 1.89 times speedup on average. Putting together track-free and SIMD increased average speedup to 3.47 times. To summarize, in this work, we present Mitra, a multi-instance graph traversal framework. It is designed for composing multi-instance graph algorithms. Mitra framework features ease of programming, optimization, expressiveness, and performance. Underlying Mitra is the frontier ranking model that abstract traversal logic to vertex ranking process and express computation logic in edge function. That's all for my presentation, and thank you for listening.